We're going to be looking at the proof of the tan-chord theorem today, but let's just quickly have a recap. What does the tan-chord theorem says? It says that the angle between the tangent, which in this case is PQ, and a chord. So we can choose the chords that join to that tangent, either AC or AB. I'm going to look at AC for the moment. So the angle between the tangent and the chord is equal to the angle subtended by that chord in the alternate segment. So what angle is subtended by that chord, but on the opposite side of A1? Well, that would be angle B. So the tan-chord theorem states that the angle A1 is equal to angle B. Alternatively, we can go back and say, okay, there's another angle between the tangent and the chord. If we look again at the tangent and we look at the chord AB, then we're talking about that angle there, and the tan-chord theorem will say that that angle is equal to angle C. In the alternate segment just means that the angles are on opposite sides of the chord. So in this case, they're on the opposite sides of that chord there. So let's start with the proof. We're going to prove angle A1 is equal to angle B. There are three different possible constructions, in other words, three different ways we can do this. I'm going to talk through them. Try and follow what I'm saying. You will find one of these formal proofs in your textbook, and on the next page I've also got them written out nicely for you. Okay, so my first type of construction is to draw a line from A, but through the center of the circle, and then join that point to either B or C. It doesn't actually matter. Let's go with C for the moment. Okay. Now, let's just give this point a label. What haven't we got? I'm going to go with D. Okay. So we want to prove A1 equal to B. So what it's a good idea is to let either A1 or B equal X. It doesn't really matter. I'll start here and say that one's X. Now, in this particular proof, we're going to look out for a couple of things. We're going to look for the fact that the radius is perpendicular to the tangent. So when you're writing down your proof, these things will come up. We're going to look for angle in the semicircle, which was why it was very, very important. When you did your construction, you had to stipulate that your line that you constructed went through the center of the circle. So AOD is a diameter. Okay? And the other thing we're going to use is angles in the same segment. And remember, what we're trying to do is get angle B to also equal X. So if we start, well, let's look at the rad perp tan. Well, that would mean that that angle's 90. The angle in the semicircle would mean that is 90. Angles in the same segment means that B is equal to D. So what we're really thinking is, okay, well, that means that I need to get D to be equal to X. Well, that's not difficult at all, because A1 is X. You've got your right angle right next to that, which means this angle here, and I hope I can fit in here, is 90 minus X. But you now have a triangle, and the angles of a triangle add up to 180, so D is X. Well, that was good news, because that means that B is X, angles in the same segment, and voila, A1 is equal to ABC. Okay, my alternative construction was still to draw your line from A to D, but make sure that you mention that it goes through the center. In other words, it forms a diameter. This time, instead of joining D to C, I'm going from D to B. Now remember, we still need to prove that A1 is equal to this angle here. Sorry, that's caused a bit of trouble. A1 is equal to that angle there. Lost my D as well. Okay, so if you like, you can call that one X this time, or again, you can prove A1 is X. It really doesn't matter. But again, we're looking for the following. We're looking for angle in semicircle. And obviously, that would be the whole of B. We're looking for the rad perp tan. And obviously that would be either side of here. Okay. And I know that we're going to go angles in the same segment. So if you like, you could say, okay, well, that one there is x, which means that one's x, angles in the same seg. And by now, you've hopefully realized, well, if that little one is x and b is 90, then ABC is 90 minus x, and A1 is 90 minus x as well. And hence, CAB and ABC are both 90 minus x, so we've proven what we had to prove. All right, here's my alternative proof, and I did see that this one's in the textbook, and that is that you're going to join from, instead of doing right through the diameter, you're just going to join O to A, and then you're going to create an angle at the center, so we're going to join O to B. Sorry, that was a bad idea. I need to remember that I actually want to prove A1. So I'm going to join O to C. If I was trying to prove BAQ equal to angle C, then it would have been a good idea to join O to B. All right, again, let's look out for what we're wanting. We're wanting to get angle B equal to angle A. Now, since I've created an angle at the center, I immediately am thinking, well, hold on, it's a good idea then to make BX, which means angle O, will be 2x, angle at the center. So in this case, we construct radii when we start. So my construction was the radii. And obviously you'd write down that it was OA and OC. We let B equal x, and then we used angle at the center to get the 2x at the middle there. But now don't forget we've created radii, and radii are equal, so we've got an isosceles triangle. And the angles of an isosceles triangle, you've got two equal angles, which means these two little ones here that one and that one, are going to be 180 minus 2x, but half of that. So what's that? 90 minus x. Which means this little angle here is 90 minus x. But don't forget, the whole of that angle, because of rad perp tan, is 90. So if the whole angle is 90 and that little dot is 90 minus x, it means A1 is x. You need to choose which proof you prefer. So either create an angle at the center or create an angle in the semicircle and angles in the same segment. I'm going to go over the page. You'll see here both of those two optional proofs are written out nicely for you. If you want to press pause, just stop for a moment, read through it, look at the layout. The mark allocation is from one of the latest exams. You'll see that was paper 3, November 2011. Obviously, that will now go into paper 2, no longer paper 3. But that will just show you the mark allocation if you're interested. So pause, read through it, and then restart your video. All right. What I'd like you to do now is, again, just listen to my instruction first and then press pause. I suggest you copy the sketch and try and prove the theorem again using a similar sketch but different letters. So press pause. When you're done, you can continue the video. Okay, now you'll notice this sketch looks slightly different. You've got an obtuse angle at the tangent instead of an acute angle. So my triangle ABC is to one side of O instead of surrounding the center, which we've seen in the previous sketches. So again, I'll just run through a couple of different ways to prove it. This one I'm starting by constructing a diameter AD, and then I'm going to join D to B. Okay, now again, you'll have noticed that I've created an angle in the semicircle is one option. Okay, don't know if that's a great option, but I have created an angle in the semicircle. So one's thinking like that. I don't know if it's a good idea, but we'll see. We've also got that's 90 over there, rad perp tan. We'll see where we go with that. Now remember that I'm trying to get this entire angle. Maybe I should just create a letter over here for us. What have I got? A, B, C, D. Let's just make this E. We're trying to prove that EAB is equal to angle C. So it's a bit tricky. It's trickier than we're used to. So it's that whole angle there is equal to C. Well, we've got part of that angle is A, so let's call that X. So the angle we're looking for, EAB, is 90 plus X. So we're going to keep that in mind. So what we're trying to get is C to be 90 plus X. Now, if we look at this triangle here, we've got a 90, we've got an X. Now remember, the angles of a triangle add up to 180. So this angle over here is 90 minus X, angles of a triangle. You'll notice I've taken quite a different approach to the previous sketch. Now, you have a cyclic quad. Let me just highlight that for you. Here's a cyclic quad. And what do we know about opposite angles of a cyclic quad? Well, the opposite angles of a cyclic quad are supplementary, which means angle C is 90 plus X. And notice that that's what we were trying to get. So both EAB and C are 90 plus X. Okay, so an alternative construction would be, again, to construct the diameter, so A to D, making sure you're going through O. And then, again, we're wanting to prove the whole of C is equal to EAB. Let me just erase that part. I forgot to do that, so I'm not sure if we're going to land up with 90 plus X again. Okay, so let's see where we are. Now, this time you'll notice I've created angles in the same segment, but before I go to that place, I'm going to say, well, hold on, I've got an angle in a semicircle over there, I've got the rad perp tan over there, and guess what? Angles in the same segment, those are both X, so guess what? Again, whole of C is 90 plus X, whole of EAB is 90 plus X, and that's exactly what we wanted. So that one's an incredibly easy way to go. Okay, the last option is, instead of creating a diameter, is to join OA and OB. In other words, we created an isosceles triangle. It's a little bit trickier, but remember, if you see an isosceles triangle, where you're really going to, well, you're wanting to say that my base angles are equal, so I'm going to call them both X. Remember, that's a 90 over there, so EAB is 90 plus X yet again. So we're aiming for C to be the same. So how am I going to get there? Well, angles of a triangle are 180 degrees, so that angle AOB is going to be 180 minus 2x. Okay, so we should all be happy with that, which means reflex AOB is 360 minus that, so that's going to be 180 plus 2x. So this angle over here is 180 plus 2x. But remember, in the previous sketch, I said when I created that, I created an angle at the center. And remember that the angle at the center is 2 times the angle at the circumference. And in this case, because of the way the sketch is drawn, it's the reflex angle at the center. So reflex AOB is equal to double angle C, which means angle C is equal to half of 180 plus x. Sorry, 180 plus 2x, that was careless, which is 90 plus x. Angle at the center. So guess what? EAB and C are both equal to 90 plus x. So that's the end of the video. Make sure you learn your proofs. Remember, it's easy marks.